1.7 The surface of the Moon. When Galileo first pointed his telescope toward the Moon, he saw two different types of terrain, dark lowlands and brighter, highly cratered highlands. Because the dark regions resemble seas on Earth, they were called Maria. Mare, in Latin, equals sea. Today we know that the Maria are not oceans, but instead are flat plains that resulted from immense outpouring of fluid basaltic lavas. By contrast, the light-colored areas resemble Earth's continents, so the first observers dubbed them terrae, Latin for land. Today, these areas generally referred to as lunar highlands because they are elevated several kilometers above the Maria. Together, the arrangement of terrae and Maria results in the well-known face of the Moon, sometimes called the man in the moon. Impact craters. The most obvious features of the lunar surface are craters. They are so profuse that craters within craters are the rule. The larger ones are about 250 kilometers in diameter, 150 miles, roughly the width of the state of Indiana. Impact craters are produced by the impact of rapidly removing debris, such as meteoroids, asteroids, and comets. This phenomenon was considerably more common in the early history of the solar system than it is today. By contrast, Earth has only about a dozen easily recognized impact craters. This difference can be attributed to Earth's atmosphere, erosion, and tectonic processes. Friction with the air burns up small debris and makes large meteoroids smaller before they reach the ground. In addition, evidence for most of the craters that formed in Earth's history has been obliterated by erosional or tectonic processes. The formation of an impact crater. Upon impact, the high-speed meteoroid compresses the material it strikes. Then, almost instantaneously, the compressed rock rebounds, ejecting material from the crater. This process is analogous to the splash that occurs when a rock is dropped into water. Craters excavated by objects several kilometers across often exhibit a central peak, usually seen in a large crater. Most of the ejected material, ejecta, lands in the crater or nearby, where it builds a rim around it. Depending on the size of the meteoroid, the heat generated by the impact may be sufficient to melt some of the impacted rock. Astronauts have brought back samples of glass beads produced in this manner, as well as rock formed when broken fragments and dust are welded together by the heat of an impact. A meteoroid only 3 meters, 10 feet in diameter, can blast out a 150-meter wide crater, 500 feet. A few of the large craters, such as Kepler and Copernicus, formed by the bombardment of bodies a kilometer or more in diameter. These two large craters are thought to be relatively young because of the bright rays, splash marks, that radiate outward for hundreds of kilometers. Highlands and seas. Densely pockmarked highland areas are made up most on the lunar surface. In fact, most of the backside of the moon is characterized by such topography. Only astronauts have directly observed the far side, because the moon rotates on its axis once with each revolution around Earth, therefore always keeping the same side facing Earth. Highlands consist of an apparently endless sequence of overlapping craters. Indeed, the great number of impact craters is evidence of the moon's violent early history. This activity crushed and repeatedly mixed at least the upper few kilometers of the lunar crust. As a result, the highlands are very rugged. The highlands are made of plutonic rocks that contain over 90% plagioclase feldspar that rose like scum from a magma ocean early in lunar history. Maria, on the other hand, are composed of volcanic rocks with a mafic composition, similar to flood basalt on Earth. The dark, flat Maria make up only about 16% of the moon's landscape and are concentrated on the side of the moon facing Earth. More than 4 billion years ago, asteroids having diameters as large as the state of Rhode Island excavated several huge craters on the lunar surface. Because the crust was sufficiently fractured, magma began to bleed out. Apparently, the craters were flooded with layer upon layer of very fluid lavas, resembling those of the Columbia Plateau in the Pacific Northwest. In most cases, these lavas welled up long after the craters formed. It seems that volcanism occurred because the crust was thinner and more fractured in these regions, rather than because of heat generated by the impact itself. Weathering and erosion. The moon has no atmosphere or flowing water. Therefore, the processes of weathering and erosion that continually modify Earth's surface are virtually lacking on the moon. In addition, tectonic forces are no longer active on the moon, so earthquakes and volcanic eruptions do not occur. However, because the moon is unprotected by an atmosphere, a different kind of erosion occurs. Tiny particles from space, micrometeorites, continually bombard its surface and ever so gradually smooth the landscape. Both the Maria and Terrae are mantled with a layer of gray, unconsolidated debris derived from a few billion years of meteoric bombardment. This soil-like layer, properly called Lunar Regolith, is composed of igneous rocks, breccia, glass beads, and fine lunar dust. In the Maria that have been explored by Apollo astronauts, the Lunar Regolith is apparently just over 3 meters or 10 feet thick.